In this mini lecture of the Soil, Slopes, and Streams series, we'll talk about river form and flow. Specifically, we'll cover drainage patterns, the geometry of channels at individual points, and also a little bit into how rivers change. River networks can take many different forms, and the patterns by which tributaries flow to join larger order streams to even larger order rivers can be quite distinct in different settings. Dendritic patterns, such as we see here from a river in Siberia, are likely the most familiar to you, and they develop where geologic structures don't vary strongly or rock types aren't highly variable. Parallel drainages typically develop from flow that extends from a simple ridgeline or plateau, such as you see in these small streams extending from a ridgeline in Iceland, or as you can see in the lower tributaries of the Lungwebunga River in Angola that extends off of the southern African plateau. A radial pattern like the one seen on this volcano in Russia forms where streams flow off a central high point. Importantly, each of these patterns is largely a reflection of the underlying tectonic conditions or geologic structures, which is why you can imagine that drainage patterns are so diverse across Earth. When we characterize river form and flow, we use a number of terms that I'll identify here. These are velocity, discharge, stage, and sinuosity. Velocity is how fast a river is flowing. It varies with depth into the water and across the channel width. Velocities tend to be slowest near the base and sides of the channel where the water contacts the riverbed, and you can see this in the video here, especially if you look towards the lower half or the downstream section of the river. The flow is fastest in the middle of the channel. The roughness of the bed is also important as it influences friction and turbulence of the flow, and this boulder-strewn stream has a very high roughness, which should generally impede flow. However, two other things matter: the stream gradient, which is how steep the stream is, and how much water is being moved. Both of these are high in this video. This amount of moving water is the river's discharge. Specifically, you can think of it as the time it takes for this column of water to move across its length. For this reason, discharge is calculated as the cross-sectional area times the velocity of the moving water. Of course, velocity varies across the channel and with depth and downstream. So to understand discharge in a channel, one has to consider and calculate both the cross-sectional variation in velocity and the cross-sectional changes in depth along the channel width. Imagine that these have to be measured in each of the vertical columns of the cross-section you see here in order to characterize the average flow of the river. Now, discharge also varies over time. For example, during a storm event, as more water enters the channel and must flow through it. So both the velocity and cross-sectional area might increase in a flood as discharge also increases. The height of the water surface in a river is called its stage. This number is typically measured above some arbitrary point, and because the point is arbitrary, this measurement can be somewhat confusing. Sometimes stage is measured as altitude, or sometimes it's the height above a point near the riverbed that a hydrologist or geomorphologist is taking measurements from. Stage is different than depth because stage is a single value characterizing the height of the water level at this cross-section. while depth is variable across the channel's width. It's thus more difficult to characterize. If a river floods, then the stage changes, much like we've seen for discharge and velocity. Downstream and cross-channel variations in velocity, slope, depth, and discharge are really important for characterizing how water moves and how water is able to move sediment. All of these change during floods. Now, streams don't often take a straight path. Nature hates a corner, few things are perfect lines, and rivers typically curve about. The sinuosity of a stream describes its tendency to meander. The sinuosity is calculated as the stream length versus the valley length, or here in this image, it's the length of the blue streamline divided by the straight line. Streams are self-organizing systems, and if you begin with a straight channel, and if the river is able to move the sediment and bed that it flows over, then sinuosity will increase naturally. We can see this in the next video. This short clip nicely highlights river sinuosity. You're looking at a map of the Grand River in Missouri. You can identify river meanders in this sinuous system and also in the flyover aerial image. In this aerial image, note the agricultural fields and farms that are adjacent to the stream. Now the view is joined by an overhead shot of an M-River stream table. This is a model by Little River Research and Design. Watch how a meandering river forms and sinuosity develops from a straight channel. You only have to start with a small instability to begin eroding one side of the channel and depositing on the other. This makes the channel migrate and curve. Pause this video, follow this link to learn more about how river sinuosity develops. There'll be a short quiz.